Hey all, I'm Avalon Feiler, and today let's talk about white dwarfs and planetary nebulae. First of all, you're probably wondering what a white dwarf is. White dwarfs are what medium to small stars, ones up to about 8 times the size of our sun, turn into at the end of their cosmic life. After a series of expansions and contractions, the star becomes a red giant and eventually a white dwarf. White dwarfs are incredibly dense, containing about half of the mass of the sun in a celestial body roughly the size of Earth. In fact, it's so dense that it's only surpassed in density by neutron stars and black holes, the result of much larger stars at the end of their lives. In addition, and as a result of being so dense, white dwarfs also burn amazingly hot and give off lots and lots of radiation. This radiation is also what makes a white dwarf's planetary nebula glow so beautifully. Planetary nebulae consist of gas blown off in the outer shells of the red giant and are made up of mostly hydrogen but also have oxygen, nitrogen, sulfur, and other elements. These gases, interacting with the white dwarf's radiation, create different colors that we see. Even though hydrogen makes up most of planetary nebulae, oxygen glows much brighter than the red glowing hydrogen, and thus planetary nebulae are usually green or blue glowing. Nitrogen and sulfur emit red like hydrogen, making planetary nebulae variant and always gorgeous. Not only do planetary nebulae come in vastly different colors, they can also form into different shapes around their white dwarf. While one might expect the gas shells expelled by the red giant to form circular patterns, many planetary nebulae are found to be elongated, spirally, or with tendrils and jets pointing out. We found that these patterns can be a result of binary stars rapidly orbiting each other very closely, or, more commonly, huge planets that orbited the original star still orbiting while burning up inside the expanding gas shell of the red giant and changing the shape of the planetary nebula. Since the gas in planetary nebulae is still expanding, eventually it will become too thin to glow brightly and will fade out of view. This happens in a matter of 1,000 years, which means that planetary nebulae are a very small snapshot of a star's life, which means that all the pictures we take of planetary nebulae are kind of like screenshots of a star's 7-second snapshot. Unlike a 7-second transitory picture, though, studying a white dwarf planetary nebula can tell us a ton about the life of a star. White dwarfs can also tell us about the age of the universe. When a white dwarf burns out, it will become a black dwarf, which won't emit any energy. So far, no black dwarfs exist in our universe, because it takes tens or possibly hundreds of billions of years for a white dwarf to become a black dwarf, and our universe's oldest stars are only about 20 billion years old. By studying how long white dwarfs have been cooling, astronomers can learn more about the age of the universe. Not all white dwarfs will even turn into black dwarfs, though. White dwarfs in a binary system can have a gravitational pull strong enough to gain mass from its neighboring star. And when a white dwarf gains enough mass to reach its Chandrasekhar limit, it explodes in a thermonuclear supernova. White dwarfs, while small, are important for studying our universe, and their beautiful planetary nebulae paint our skies with the history of the stars they surround.